So I'm recording. Can you hear me? Hello, is there some issue?
I can hear you.
Good. Okay. Um, do I need to do anything else to get things started? I'm just, and you can see the screen, this screen. Can you guys see this screen?
Yep.
Okay. All right, good. So I think I'm recording, and so I guess we can basically start. Technically, well, I guess it's already 5:30, so we can start now. Let's start with questions. Some student might have a question. This is technically a 468 class, but we can make it a hybrid class if you want. I'll be putting I'm not sure where I'm going to put the video, but in as much as you guys your faces don't show up. And anyway, if you just use chat. Okay, so there's a question about problem 7.19. So let me first of all find 7.19. And, oh God. All right, so this is the standard way to solve find the energy eigenvalues of a hydrogen atom. So basically you'd just like to see me do this one. All right, so let's see if I can, I'm looking up the solution here, because if we have me do it just straight, I'm liable to get signs wrong and fumble around for a while. So right, so this is, yeah, I think this was quite a legitimate question to ask, because this is in fact somewhat long. So I'm going to move something to here. So presumably you can see, let me get rid of this damn thing. So you can see, here's the, let me make this bigger so it's easier to see. And so we'll go through this so I'll go through 719 in detail. It's an important thing to know about, because it's a real physical problem. Okay, so we've got a hydrogen atom. This is the potential. I've been using SI units in this book, although I very rarely use them when I'm actually doing physics myself. But one can rewrite that as minus q squared over r, where q squared is e squared over 4 pi epsilon 0. And E, of course, the charge of the electron. So this is the electrostatic potential. And then the equation, it's here labeled as 7.514. I assume anyway, it's this equation, so I don't need to have the number exactly right. So this is the second order ODE that we've got. And in fact, it's already in self-adjoint form. But now if we look at it, well, first of all, this is on an infinite interval from 0 to infinity, where R goes from 0 to infinity. And if we look at it at big R, well, let's look at it at big R. At big R, we've got R squared multiplying these derivatives here. R squared multiplies, notice, the second derivative of big R, because when the derivative acts on the r squared term, you get a term proportional to the first derivative of big R, but it's only multiplied by 2R. So the important term at big R is R squared R double prime. And then if we look over here, what's big at big R? Well, this term is multiplied by R squared. This term isn't. This term has a 1 over R. So the actual big terms are R squared R double prime plus 2m over h bar squared ENL times R squared times R equals 0. And so we get this equation. And that's an equation that's easily solved as an exponential. That's e to the minus something times R. And you differentiate twice, you just get, this thing just becomes minus 2m e over h bar. And that gives you this. Right, okay. And we get an h bar squared actually when we differentiate twice. So we know that R goes like this at big R. At small r, what are the important terms? Well, there's a 1 over R term here. And on the other hand, it's multiplied by R squared. So the important terms are R squared times this double derivative equals LL plus 1 times R. And what's important here is two R prime is L plus 1 R. And the solution there is that RNL is R to the L. And there's also a factor of 2m over h bar squared. I'm ignoring overall constants here. I'm just trying to get the R dependence correct. And so we have R to the L. So what we do then is we take this R, the solution to this equation, and we write it as small r behavior times large R behavior times something that is that behaves in a modest way at all values of R. And then we apply the method of Frobenius to find the eigenvalues of energy for which R is suitably smooth and normalizable and so forth. To make things, to make the calculation easy, we set beta equal to this square root. So we've got R is R to the L e to the minus beta R times some PNL of R. And let's see, I can make this even bigger, I think, actually. So then we just compute this term. And of course, we have to differentiate R to the L and e to the minus beta R. And when we do that, we get this expression here, which is fairly big and messy. We then set B equal to this quantity, 2mz q squared over h plus z is the charge of the nucleus. This calculation works for example, singly ionized helium, doubly ionized lithium, and so forth. And so this equation becomes considerably simpler. And now we carry out the differentiation. And now we finally get to this stage. When we're at this stage, we can get serious and do Frobenius's method. And so we let it equal R to the K times this sum. Then we get this expression. We set the lowest power of X equal to 0. So this gives us the 2 two roots for K. We find K equals 0 or K equal minus L plus 1. So we choose the larger root, K equals 0. We then substitute that value of K back into this equation here. And it's a little bit simpler now. It looks like this. Or at first it looks like this, but let's see, we can shift the index n here on these terms and leave it alone on those terms. And notice that the term n equals 0 and n equals 1 would cancel. Those terms, some of those terms cancel, and then we can rewrite that like this. That gives us this as a recursion relation. An plus 1 is this thing times an. If we go to large N, this turns out to be something like this. And that is an increasing exponential. And it would be divergent because it's e to the 2 beta r, and we only have suppression by e to the minus beta r. So we require that this thing terminate. And that means that b minus 2 n plus l plus 1 beta must equal 0 for some value of n. And well, that tells us that beta, which we defined in this way in terms of the energy, is b over 2 l plus n plus l plus 1. And that then gives us this expression. And if we unravel this, we get the energy eigenvalues like this, which is the correct answer. For the binding energy of an electron. And a nice way to think about this is mc squared is the rest energy of the electron. So the energy levels are minus a half mc squared times z alpha squared over some integer squared. And the integer is the sum of n plus l plus 1. I don't, let's see, we can have L equals 0. I think we can have N equals 0 also. Well, yeah, certainly. And it's I said, right. Let's see. Right, yeah, okay. So that's right. N and L can both be 0, and then they increase at 1, 2, 3. Let's see if this, well, it's also true that it turns out that L can't be bigger than N. All right, so that's the whole 9 yards of that particular homework problem. There may be questions, or it may be that you want me to do something else or explain something else. I mean, in these first 7 chapters, there have been an awful lot of concepts, and you may want, all right, a hint for 732. All right. Well, what you've got to do here is, all right, the first step in the hint is you use this equation, P is W rho. And so let me maybe pull this in, just do something very simple here. Okay, so what we've got here is that the pressure is some constant W times the mass density. And so the conservation law is d rho dA is equal to minus 3 rho plus P over A, but that's minus 3 rho plus W rho over A. And so that's minus 3, 1 plus W rho over A. And so that then is an equation d rho over rho is equal to minus 3, 1 plus W dA over A. So I hope you can integrate that equation. And when you integrate that equation, you should be able to derive this equation here. So that's too much of a hint. I shouldn't give you these huge hints, but because you need practice doing problems like this. But anyway, there we are. What is a bar and rho bar? Good. Yeah, they're just numbers. They're just constants of integration. So they're exactly, they're just constants. So do we have another question? Oh, I see. All right. Well, I should maybe have said that these were constants. Okay, let me make a note to maybe make that clearer. Okay, what else? We shouldn't just have you staring at me. You should ask me to do something, and then I'll try to do it. Try to explain something. Well, if there are no further questions, then why don't I say something about integral equations? So here's a first order differential equation. P is a known function, Q is a known function. We're looking for the solution U. And what we can do is we can integrate this equation. And when we integrate it, we get an integral equation. And so if we integrate this differential equation from A to X, what we get is that U of X is U of A plus the integral of these two terms, which are P of Y, U of Y dy plus the integral of Q of Y dy. And now Cauchy was a very, very smart man. And he invented all sorts of identities. And in particular, he has a formula for repeated integration. His formula for repeated integration is this. And if we just use the simplest case of it, what you can show, and this is exercise 8.1, is the integral from A to X dz of the integral from A to Z dy f of y is the integral A to X of the quantity x minus y f of y dy. And so that's a very general, and when I look at it, I must say, I find it puzzling and surprising, but it's nonetheless true. And in fact, I may well assign this as a homework problem. So if we apply this formula to this, the integral of this first order differential equation, or actually we're going to apply it to the second order differential equation, namely u double prime is pu prime plus qu plus r. And then what we find is that u is some function f of x, which is this expression here, plus an integral of something that some people call a kernel, k of x and y, u of y dy, and that k is p plus x minus y, and you see the x minus y is coming from here, times q minus p prime. And so there we've got basically a solution of the second order equation expressed as in terms of the known function r, the known function p, and then we have to do the integral. But of course, this isn't the answer, because you see, we've expressed the unknown function in terms of some known thing plus a kernel, a known kernel, and then here we've got the unknown function again. So this is not actually the total solution. This is just how you transform, how a second order differential equation looks when you've transformed it into an integral equation. And, but there is something that's very simple about this, namely that you see this thing here, if you imagine taking the interval from a to x and dividing it into, say, 100 points, or splitting it up into 100 subintervals, then you could numerically approximate this as being the sum of, effectively this would, K would be 100 by 100 matrix, U would be a 100-dimensional vector, and the same thing for F, and then we'd have U over here. Well, this is something you can solve, and MATLAB could solve it for you, or you could write a program in C, Fortran or something, or you could go to, what is that, Python, and solve it that way. So in some physical problems, integral equations arise independently of differential equations, but, and whatever they are, they have properties that are more suitable to mathematical analysis. And the reason is that derivatives, the derivative of a function is more singular than the function in general. Now, sometimes it's equally singular. The derivative of an exponential is just an exponential. But for example, the derivative of this function, a step function, and if this is 0 and this is x going this way, then this function is theta of x, which is 1 if for x greater than 0, and 0 for x less than 0, and it doesn't matter what you call it at x equals 0, because that's, you know, a set of measures 0, and look at, we know that doesn't, Lebesgue told us that didn't matter. So what's the derivative of this? Well, dx of theta of x is Dirac's delta function. So this is very singular. So that's why mathematicians love integral equations, because they there they can apply their mathematical techniques. And another reason is that in this case, you see, because the equation is linear, you can just turn it into a linear algebra problem. All right, so let's see. You guys may want me instead to talk about or explain something else, another hint, or something that was confusing. Let me ask you also a question. Are you guys able to see the new class website, which I think I've sent you all a link to that new website. And let's see. Okay, so let me see if I can remember myself what the link is. It's panda3.phys. Right, I think this will do it. No, that gets us to, that's too general. Let me go back to Panda3.
I put it here in the chat. We're good.
What's that? You're saying that? Oh, thank you. Right. Okay. You guys are great. Let's see if I can copy this. So this is the link here. And all right. So have you guys been able to get to this and the homework assignments and the links to the videos? They're all there. And I'd ignore the 2019 webpage. Just look at the 2021. So you guys have all been able to get to this?
Yep.
Okay, good. All right, I was just checking. So let's see, is there a question or should I plow on and say some more things about integral equations? All right, let me, these things are basically definitions. So one type of integral equation looks like this. And as I said, K is a kernel. There's a f of x is a known function. And what you're trying to find is what's u and what is the eigenvalue lambda. And this is called an inhomogeneous Fredholm equation of the second kind for a function u of x parameter lambda. And if f of x equals 0, well, then it's called a homogeneous Fredholm equation of the second kind. And this equation has nice solutions only for certain eigenvalues lambda, and each solution we say is an eigenfunction. Now, one special case is if lambda is equal to 0, but f is not equal to 0, then it's an inhomogeneous Fredholm equation of the first kind. And if both lambda and f are equal to 0, it's a homogeneous Fredholm equation of the first kind. And these things are, of course, also are all linear because they just involve u or u to the power 1 or u to the power 0, which is just a constant. Notice if you take the interval from a to b and you divide it into 100 intervals, subintervals, or 1,000 or 1,000,000, you can convert all of these to matrix equations, and you can solve them on MATLAB without any trouble. The problem is just telling MATLAB matrices are. And once you figured out how to do that, then you're basically home free. Of course, the reason why you can solve these things on MATLAB without any trouble is that they're linear. So in general, if the problem is linear, you can do it. If the problem is nonlinear, you may be able to do it, you may not be able to do it. It's just not obvious. And nonlinear problems are intrinsically interesting and hard. Okay, there was another person named Volterra, Vito Volterra. He lived slightly, he overlapped Fredholm, but was somewhat younger at the same time. So here, if the kernel is causal, that is to say, the kernel vanishes unless x is less than y. That's that theta function, which was introduced by a physicist named Heaviside, and I've always thought it amusing that this is a function that has one side equal to 1, the other side equal to 0, so one side is heavier than the other. And it's amusing that the man who introduced it was Heaviside. In any event, so lambda is a parameter, f is known, and k is known, and you're looking for lambda and u. And this is called an inhomogeneous Volterra equation of the second kind, but again, only if this kernel vanishes unless x is greater than y. If f vanishes, it's a homogeneous Volterra equation of the second kind. And typically it has, the lambda is an eigenvalue and it has nice solutions, typically only for certain eigenvalues. So if you wrote this as a matrix equation, you see, it would simply be, so let me maybe switch colors because I'm doing something a little bit different. So this equation that's integral k of x and y, u of y, dy from a to x equal to lambda u of x. Well, if you discretize things, then you've got a matrix k of xi, yj, u of yj. And then I guess one has, if this is an n by n matrix, then this would be, you'd have x minus a over n. That would be what dy would be. And this would equal lambda u of xi. So this is a matrix equation. And that's why this is an eigenvalue equation, basically of the form ku equals lambda u, where u is a vector, k is a matrix. And there's a scale factor here that I left out. On the other hand, if you set the eigenvalue equal to 0, but f not equal to 0, then this is an inhomogeneous Volterra equation of the first kind. And in that case, the algebraic, the linear algebra analog is ku equals f. Well, if k is a non-singular matrix, then this the solution is u is just equal to k inverse f, k being a square matrix. Finally, if both lambda and u equal to 0, it's a homogeneous Volterra equation of the first kind. And so it's an equation of the form ku equals 0. And So this is effectively an eigenvalue, an eigenvector with eigenvalue 0. These equations are linear because they only have u. They don't have u squared or log u or e to the u or 1 over u. And the Volterra equations are, of course, a special case of the Fredholm equations. And so here we can just talk about just the Fredholm case, because the other case is a special case. Now, since these equations, so let's see, I'm surprised I'm not getting requests for more hints or requests for an explanation of something that we covered in chapters 1 through 7. But if not, I'll just stagger forward through the rest of chapter 8. Chapter 8 is a very short chapter. That doesn't mean the subject's trivial, but it just means that I didn't really have that much more to say about the subject. So let's because they're linear, you can add solutions. So at least you can add solutions of the homogeneous equation. So for example, if u1 and u2 are eigenfunctions with the same eigenvalue, then the sum with arbitrary coefficients is also an eigenfunction with the same eigenvalue, because k uj is lambda uj, and so this is equal to that. It's also true that the difference of any two solutions of one of the inhomogeneous Fredholm or Volterra equations is then a solution of the homogeneous equation. So if you have if for j equal to 1 and 2, you have a solution of this equation. I'm a little confused as to why I have a superscript I here. I think that may be spurious. Anyway, the difference then, u1 minus u2, certainly satisfies the homogeneous equation, because then f cancels. And so now what we see is that since these were arbitrary solutions of the inhomogeneous equation, you can write the most general solution of the inhomogeneous equation is a particular solution. In other words, any old solution of the inhomogeneous equation plus the most general solution of the homogeneous equation. And so this is one of the reasons why linear equations are much easier to solve. The other reason in this is that as I mentioned parenthetically, and as I'll now say in a little more detail, you can translate them into linear algebra problems. And once you've got something in linear algebra with modern computers, there's no question about it being soluble. So if we break the real interval into n segments of equal length, and that's what I did over here, actually. So delta y is b minus a over n. And so y0 is a, yk is a plus k times delta y, yn is equal to b. And if we also set xk equal to yk, that is to say, we're imagining those values of x as well. We're labeling the x's the same way. So we're dividing the square of side B minus A, and the points are then xk and xi and yj, say. Anyway, we can define capital U as a vector so that U sub k is just U of y sub k. K then is an n+1 by n+1 square matrix. So this is what I was doing in a, oh God, it wants a face ID. Whoops. All right, let me get rid of that. Make the matrix X, K sub KL be the kernel. God, this is, I'm always doing this. I've never been good with names. And so here I've used the letter K for three different things: capital K for the matrix, little k for the kernel, and k for the index. I think I told you once that I was in a linear algebra course, not a linear, abstract algebra course as an undergraduate, and I did a proof, an elaborate, difficult proof, using the letter A for three different things. Got a 0 on that particular problem. I tried to explain it to the professor, who was a tough Scotch mathematician, and he would hear none of it. But so I really ought to change the, don't use K for everything. Anyway, we can approximate the homogeneous Fredholm equation of the second kind. That's 8, that's that one. We can approximate it, well, there it is, as an algebraic equation. And here, let me see, we want to get rid of that, I think. And let's see, I can make this big, the font's bigger here, so let me do that. Okay, so we're turning this equation, we can discretize this equation, and it becomes then this algebraic equation. And this is just an eigenvalue equation that MATLAB solves. You just use the command eig, E-I-G, in other words. So, and we saw earlier in section 1.27 that every such equation has n+1 eigenvalues and eigenvectors and eigenvalues. The eigenvalues then are solutions of the characteristic equation. And in general, as n goes to infinity, delta y goes to 0, the number of eigenvalues and eigenvectors, of course, becomes infinite in general. If we apply the same technique to the inhomogeneous Fredholm equation of the first kind, we get Ku equals F. So U is K inverse F as long as K is non-singular. If we apply it to inhomogeneous Fredholm of the second kind, we get this matrix equation. The associated homogeneous equation has these eigenvalues and eigenvectors. And for any lambda that is not one of the eigenvalues, K minus lambda I has a non-zero determinant, has an inverse. And so the vector U given by the inverse acting on F is a solution of the inhomogeneous equation. So now we have a solution of the inhomogeneous, and we use MATLAB to find solutions of the homogeneous equation, and we're basically done. If lambda beta is one of the eigenvalues of the homogeneous equation, then the matrix won't have an inverse, but it would have a pseudo inverse. And you can write the singular decomposition of K minus lambda I this way, and the pseudo inverse then is this, and the sum is over the positive, the singular value, the positive singular values. Some of the singular values can be 0. And if vector F is a linear combination of the left singular vectors, whose singular values are positive, then ui equal to this is a solution of that. And that's basically the explanation. And so the most general solution then is of this inhomogeneous equation is the most general solution of the homogeneous equation plus, which is to say a bunch of these, plus this structure here. And there are, as I said, programs in, well, available in Fortran C and I guess other languages that do all this linear algebra. So let's see, that I did not intend to spend so much time on integral equations. But I haven't been guided by you guys to a particular question. So is there a question? We need a question from somebody. So please throw me a question. All right, well, hearing no questions, technically this class goes another 5 minutes. So there's plenty of time for a question. If there's no question, then let me say something about integral transformations. This is a more advanced topic, but it's worth looking at. And I think, I mean, I can talk about it to you, but I think the best thing is for you to read it yourselves, because it does, it relates a bunch of things that in chapters 1 through 7 have been treated separately. So integral transformations help us solve linear homogeneous differential equations like this. So L is some linear operator with derivatives, derivatives with respect to a complex argument. So in general, we're in the complex plane here. And we've got a kernel K that's analytic in both variables. And we write U as an integral along a contour in the W plane weighted by an unknown function. So in other words, we want to solve this. And what we do is we say, well, we're going to write it this way. U is some kernel, some function V, integrate along a contour in the W plane for a given Z, and the Z only shows up here. And we want that to be a solution of this equation. So, and the differential operator here doesn't affect the contour of integration. Or if it doesn't, then the differential equation looks like this. It's L times K V plus C K V equals 0. And so now what we want to do is we want to find a linear operator, M, that acting on K. Okay, hold it, there's been a question. And I think the question's more important than continuing on this. Nothing specific, but I am curious, if we find ourselves at the end of chapter 10, before the end of the semester, what else might we get into? That's up to you. There are many things in the book, and I'd be happy to talk about any of them. What I'd really like to happen, and what I think would be really good for the students, would be for some of you to take 467 in the spring, and then in the spring we can do the second half of the book. And there in the second half of the book, we've got a whole, so what we plan to finish here is Legendre polynomials and Bessel functions. That's what we have to finish this semester. If we finish these topics early, I will do whatever you want. If you want to hear group theory, special relativity, general relativity, forms, probability and statistics, Monte Carlo methods, artificial intelligence, order chaos fractals, function derivatives, path integrals, renormalization group strings, I'll discuss any of those things either at the end of this semester or next semester in 467. So what we need is if we the quantum field theory course. Quantum field theory should be offered in the fall. If it's not being offered this fall, it should be offered next fall. But conceivably, it might be offered next spring. I don't know. I'm not the person who decides when courses are offered. The person who's most concerned with those is named Moose. As I told you, I'm terrible with names. I used A for 3 different things in that abstract algebra problem, examination problem, not a homework problem. And Musumi, she's married to Dinesh Lumba, and so her last name may be Lumba, but she may have kept her maiden name. I can't remember. Roy, yes, thank you. So Musumi Roy she's the one who organizes classes. Right, yeah, I've taught quantum field theory and I've put some of my lectures on the on YouTube. You can send email to Masumi and ask her, or Professor Roy, ask her what, when we're doing quantum field theory and so forth. But in any event, these are topics that are, some of them are useful in quantum field theory, some of them are just useful in general physics, and both theoretical and experimental, such as probability and statistics. General relativity has become more and more important because there's been, well, more and more investment in telescopes, and in particular in that LIGO project, which I never thought it would work, but it did, and has been detecting gravitational waves emitted by, typically by colliding or black holes or neutron stars colliding with black holes and so forth. And so, general relativity is much more relevant to the rest of physics now than it used to be. My approach to GR, I think, is more straightforward than most approaches. Anyway, if you've got a copy of the book, you can look at it and see what you think. So let's see, I guess class is over, but if there's another question, I'll hang around and answer it. And I would hope that you would talk amongst yourselves to choose, if we actually do get through Legendre polynomials and Bessel functions before the end of the semester, of this semester, I hope you'd somehow come to a consensus and tell me what it is as to what you'd like me to do in the remaining week or whatever it would be. You know, I'm happy to do, you know, just anything. Some of these are much more detailed than others. In other words, general relativity is a big chapter, group theory is a big chapter, artificial intelligence is a very short chapter. Functional derivatives is a very short chapter. Order chaos fractals is quite a short chapter. Same thing for renormalization. Path integrals is a longer chapter. Monte Carlo method's fairly short. All right, so I guess I'll end it, and I'll certainly put this on the other class website. So there's a class website on which I have been putting the MP4 files. I suppose I might as well put this also on YouTube, although it's not quite a standard class. Okay, well, have a nice evening, and thanks for the questions, but do ask more. It's really important to ask questions. It guides the person teaching you, and it's good for the person asking the question, and it's good for the people who had the same question but didn't think of asking it. All right, so I'll say goodbye now, and I'll do the stop share. And
Thank you very much. Have a good one.
yeah, you too. Thanks.